If you go to the YouTube channel, which is just !YouTube in the Twitch chat, you'll get a playlist for the previous 8 weeks. And then today we'll be doing number 9, which is these interesting kind of finale celebration fireworks. Nice little performance or whatever. So we'll be putting together some of the techniques from previous weeks. If you could see a few of it, like there's the shimmer or the twinkling here. So just using the same theory, same idea for the explosions of these to flicker them and stuff like that. So we'll get started in a little bit, just give people another minute or two to get in. But yeah, it should be a nice little collection, 9 weeks. I don't know, I felt like maybe doing more would get too intimidating to to try to follow them all or something like that. But yeah, so there'll be a new topic being introduced today as well, which is custom functions, like making your own function inside of Vex. And then we've pretty much covered like not everything with, there's too much to cover with Vex, but this should be, you should be a very proficient coder, or programmer, or Vex artist if you complete all 9 of these challenges or lessons. So yes, 9, we're gonna have 9 total, and each one is like 1 to 2 hours or something like that, so it's a pretty substantial thing. I think 9's also, something around 9 is a good number, just from teaching at universities and stuff like that previously. It is around the length of a semester. If you imagine like a fall or a spring semester or something like that is roughly the size of these. This was something I was working on previously from last week, using arrays and stuff like that. So this is all built using Vex to animate and even create and like fill this rectangle or the box with a bunch of smaller boxes, just using points with the scale attribute and then kind of distorting them or deforming them around and stuff like that. I'm not going to be able to get to this during these workshops because it's a little too, it's just too long to try to get through in a single session. It's like too much coding and too much programming and stuff like that. But yeah, you can really create some powerful stuff, and this runs pretty much in real time, like to generate all these boxes or all the points and everything like that. So hopefully you guys get a good sense of some of the power of Vex, the coding syntax, the structures and stuff like that. Let me know if you have any questions or anything like that. So we're even going to get into creating some colors. I didn't do it as part of the announcement banner or whatever, just because I was sticking with this minimal black and white aesthetic or whatever. But yeah, we'll be getting into a bit of that stuff as well today. Happy Sunday. Thank you, Arch2. Hope you're having a good weekend. We're getting some rain here. It's a dreary gray weekend in the Bay in San Francisco here. It's always gray. You're in Europe or somewhere north of northeast of England? Seems like this is the time of the year where England gets, Denmark, North Europe. Yeah, it seems like that area gets pretty, the sun sets at like 3 p.m., right? We're doing, Sunar, how's it going? We're doing week number 9 of this Pure Vex workshop. So we're gonna be doing these fireworks, little finale celebration display. CS Canal. Is that how you say it, or it's C-Scannel? C-Scannel? How's it going? Woo! Vex. Let's go. Yeah, so we got a nice little collection. If you do exclamation mark YouTube in the chat, you get a link to my YouTube channel, which has a playlist with the previous 8, and then we'll be completing the last one, number 9, today. You've made fireworks before? Yeah, so there's pretty straightforward ways to make fireworks. If you look at the top here, there's a fireworks shelf tool. So we're going to be looking at this just from a only vex standpoint. Like, you can make pretty good fireworks just using shelf tools and stuff like that. Not the exact same ones. Yes, most of these for the workshops and stuff that I've been doing, like obviously this, you could use an RBD solver, you would use particle solvers and stuff like that. These are more just challenges to get your programming coding skills up and stuff like that. Could you share again? If you do exclamation mark hip in the chat, there's a link to get the scripts. So there's a fetch latest, and then there's this list all, the JBRM scripted up. If you do exclamation mark hip, you'll get a link that has those tools and everything like that. So yeah, just doing the traditional shelf tool, you can see that there's you already get a pretty good starting point. But yeah, it's using solvers. You can see this cache is filled up and stuff like that. One of the advantages of doing all this stuff in Vex is if you go to even like the end frame or something like that, you can see that there's no cache. There's no kind of roll up or anything like that. So you can even add a ton of complexity and preview instantaneously like any change that you make. So that is one of the advantages of doing these kind of pure Vex, pure Wrangle workflows. Everything is computed just using math or functions or stuff like that. There's no kind of buffers or previous frame being used. So you do get a little bit more kind of feedback or quick results that way. These are pretty nice. I like the variety of the shapes. I wanted to put in some variety, but I got too lazy with mine. Mr. Vavel, how's it going? But yeah, these look pretty good. I like the colors a lot too. Planning to get into some stuff. Talking about some of the fireworks colors later today. But you pretty much nailed the chart or the example I had ready to go with the different chemicals or the different formats or whatever. All right. So I think it's time to get started. Let's go to our new file. Just going to clear it out, and all that we have is this geometry container and nothing inside of it. So we'll just make a sphere, and that will be our starting geometry, our starting point. Usually the way that we've been setting these up is with source geometry, so you have flexibility. If you want to add a grid or create more points later, it will kind of multiply or amplify the number of effects or results that you're creating. And you could make the sphere a little bit smaller just to make it less visible or blocking everything. And we'll get started just making the base kind of trajectory that a firework travels on. So usually you're familiar with like, there's the launch kind of force or the fuel or the thrust. There's gravity, and there's wind or drag or stuff like that. Those are the forces that act upon a firework or a mortar. We're just going to replicate them using some mathematical formulas. So if you remember from week 1, we made all of this bouncing just using sine waves other kind of graphing functions to get this kind of result. So if we look at, just make a line, we'll do our typical graphing calculator setup. So we have a line, we'll just set the height to the the u parameter. So we'll have a u coordinate, and that will be equal to the y position. And then we can set x. So we have a kind of diagonal line. And then if we want to visualize a function, we can visualize it like this. So we set the new height or the new amplitude using a sine function. And we'll just do a sine of u. And nothing doesn't look too different right now. We're just viewing the first portion of a sine wave. If you remember, these are using what's called radians for the unit. So you need to multiply by pi to convert into radians. So once we do that, you can see we get one section, one kind of up and down of a sine wave. If you want to go the full repetition, you can multiply by 2 pi. And then we have a squiggle. If you want to do higher frequencies and stuff like that, you can do all kinds of fun. So for a firework or for just a ballistic kind of projectile, we're not even going to be needing to use a full cycle of this. We could just chop it off somewhere up here or somewhere here, depending on when we're going to detonate it. And then we have a pretty good approximation or just a kind of mathematical representation of like a ballistic arc. Kind of like if you fire a cannonball or something like that, over time the initial force wears off and gravity takes over. So this will be the main function or the starting function that we'll use for our sphere. We'll just do p dot y equals sine of the time. So f at time, this is just your global scene time. Instead of frames, this is just in seconds. So we're working at 24 frames a second. So it shouldn't be too, if you see we have like 10 seconds in our timeline or 240 frames. So this would just repeat or cycle 10 times, which wouldn't be too fast. If we want to scale it by pi, we can do that. And let's just see what we get. GABA DSG, how's it going? So you just have this kind of bobbing pendulum or whatever you want to think of it as. Just a sine wave happening in the vertical axis. And we can just take a section of that. If we want to do like a if statement, I'm doing all right. We're getting some rain here, but nothing better to do than lock yourself inside during a pandemic and a rainstorm at the same time. Lock yourself inside and do some creative, recreational computational programming. So we have an if statement, and at least you have fireworks to entertain yourself. So we'll do an if statement. We'll say if the time exceeds 2.5 seconds, then remove or delete the point. So you say 0 for myself, the current geometry, and pt num for the current point number. So I might have made my time a little bit too long. I'm also going to, instead of changing this timer, I'm just going to reduce the frequency of the sine wave. So if I multiply this by like 0.25, it will be 25% of the speed. So it just depends on how quickly you want your firework and stuff to travel. This gives you a good sense of scale for how long it takes things to rise up and finish their trajectory. Then if we want to add some horizontal movement in, we can do that by modifying x. And we can just add to itself using plus equals. And we'll add time. And then again, I'll just multiply that by 0.25. So now we have not only upwards and downwards movement, but we also have some horizontal trajectory happening. So if we want to go like more straight up, we could just do less of a time influence over the horizontal. And then we just have kind of like straight up and down. If you want to go further, you can do this by a really big number or something. This is like a big, I don't know, maybe like a bazooka that you shot or something. We'll just stick with something closer to up and down. Let's just keep ourselves organized a little bit. We'll just move this stuff around. This will be sine function. Someone who shouldn't mess with fireworks. Yeah, this is the dangerous. Like you're shooting the Roman candle at someone. So this is like a basic trajectory. And if you guys want to get caught up, just do a share of the file. Again, if you do !hip in the chat, you'll get a link and stuff like that for how to set up shelf tools. And you can grab the scene that I just shared in a more quicker, kind of simpler fashion using that. And I'm just going to open up another Houdini session. For whatever reason, whenever I press like the up button to play, it's like tumbling my viewport, which I feel like is going to get a little distracting for you guys. So I'm just going to open up a new Houdini session and load this scene, and we'll continue on in a minute. Oof. So this is still the smaller UI. Go bigger. All right, we'll just give that another minute. So we already have a little bit of this done if we look at our template or our goal. We have the main projectile part done, and then we'll start adding in the trail, the exhaust. So we have Houdini open. And should be able to get going. All right, that one's better. So I'll just make a copy of this node to have a bit of like history of where we started, breadcrumbs or something like that. And we'll start adding the exhaust points. So if you remember from some of the previous, I don't remember which ones are the best ones, but we used for loops to create like extra children circles up here. We did it to make more threads from a single curve or a single point here. So we can do a similar idea with this. We'll just say for int I equals 0. And The stop condition will be when I exceeds, let's just start with 20, and then each loop will increment I by 1. So the shortcut for that is just plus plus. We'll do our Egyptian brackets to start and end the for loop. And then we can start putting things in here to add the points. So if you remember, we already did the remove point function, but we can also add points. If we just use add point, pont, add point, and again, we do 0 for the current geometry or ourselves. And then the next argument is the position that we want to add the points in. So if I just do something like a vector I, we should get kind of like a diagonal staircase kind of thing. So what this does is each increment of the loop, it will add these points at 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, and so on. This is a good idea just to get into different like debugging habits like this, either through the viewport visually or using the geometry spreadsheet and inspecting coordinates this way. It's like nobody just sits down and writes an entire 20 line wrangle without making like a syntactical error or something like that. So just as you're going, it's a good idea to do these little sanity checks or just make sure you're doing the thing right. And we'll do, we can start doing the same kind of idea of expressions here. So let's just start with something easy. If we say we want this point to inherit the parent point, we can do at p like this. And we have too many parentheses. You can't see them because they're all stacked up on each other. But basically, where this sphere is, we now have all of these child points that we just created. And once that goes away, you can see them. So they're all sitting on top of each other. If we want to add some gravity to this, we could subtract like time from y, like that. You can see where we have a little bit of an issue, is that these aren't getting like the correct, they're not inheriting the position that we want them to start at. So what we actually need to do is kind of recreate some of the work we did earlier and use these functions again to kind of say where should these points end up at, if that makes sense. So we'll say this would be our trail position, and we can just start it at 0 like that. And then when we add the point to the geometry, we'll just add it like that. So we're just saying they're at 0 and not doing anything with them yet. And then what we can do is use our same functions. So the trail position dot y with a height will be equal to this same thing right here. So we've copied the vertical movement, the height, but we haven't copied any of the horizontal motion yet. So we can just grab this same function here, the same line of code, and add this to the x component of the trail position. Dot x. And then we have them. So if we start to try to do our gravity now, we can try to do that with the y position or the height. We'll say minus equals at time. So again, you can see we have the same problem. And what we actually need to do is, instead of updating this first sine function using time and the x at time, what we actually want to do is calculate them from a fixed constant number. And that would be like when this trail point is born. So if we go back here, we're basically going to figure out ahead of time where is this trail point going to start from, and then kind of backtrack from there. So if we, instead of saying time, let's just say we have a trigger time, and that will equal like a random number that will generate using do the point number, but we also want to include I, so that this is unique for each iteration of the loop. So we'll just say I times some number, and we should be good. So now, instead of constantly updating where the trail position is going to look at, we can just use this trigger time. And again, here we can use this trigger time. So you can see already we've figured out like where the start of these trail points are going to be. And then if I add gravity, these fall down like that again. So even our gravity is a little bit messed up. What we want to do is actually subtract from time the trigger time. So we're actually going to find like the difference. And this looks a little bit weird because it's kind of starting at a negative number and then crossing 0 and going positive. If you want to clamp it, you can do that using the max function. So if we do max, this will use the highest number of either 0 or the result of this operation. So basically, when this is a negative number, it will just use 0 instead of the negative number. And now, once my main firework or the main projectile passes these, it's kind of like they're being emitted or created. And it's possible my gravity here is a little bit too strong. The vexed session. No, it's not taken by busy work. Yes, I'm free for the weekend. I'm released. But yeah, sorry I couldn't make the cool zone on Friday. I wasn't cool enough for the cool zone. I wasn't in the chill zone yet. So this is going to be our gravity. If we want to not have these fall down as quickly, what we can do is just multiply this by like 0.1 or something like that. And then you see they fall down a little bit more slowly. And the other thing we want to do is make sure that we're not showing these points before they're going to be emitted or created. I'll just shrink the main thing down a little bit so it just looks a little bit like what we're after. So what we can do with this add point, we can say if the we want to check if the I think this is right. Trigger time is, let's just think this through. If it's greater than the current time, less than. So if time has surpassed when this point is supposed to be born, then we'll go ahead and draw it or create it. All right. And then you can see that these stop running at a certain time. And that's just happening because our trigger time is just getting generated using a random number. It's always going to be between 0 and 1. So up here, our firework is going to live for 2.5 seconds, but we're only triggering trail points from 0 to 1 second. So we can multiply this by something like 2.5, if we want to match it exactly. And then we have enough of them to last. So it's pretty cool. We can do, let's think what else we can do. We can increase this and make a lot more of them. If we want this to look a little bit more realistic as well, we can start to kind of shoot them outwards, kind of like diffusing them outwards or blurring them. So it's like they're getting shot out like exhaust in a little bit of random directions. So, C-Lore, how's it going? Yeah, just give me a second. So I'll do one more example here, and then I'll do a share of the scene. You can also get them if you're joining late or anything like that. You don't see them in the chat. If you use the shelf tools, you do !hip, there are some shelf tools, and you can actually get like a nice list and everything like that. But I'll update it in a second. So if we want to diffuse these points out like uniformly, we can use this function that we actually used from the 4th week to make this sphere. So you can set the position and then use sample sphere uniform. And then the position that I want to sample the sphere at, I just want it to be random or unique for each point number. So now we have random points on a sphere. And if we want these all to be the same length or the same distance from the center, we can use a special function called the normalize function. So if we check the results there, what this does is just make the lengths of the vectors unit or 1. So the distance from the origin will be 1 for all of these points. So I'll go ahead and do a scene share, and then we'll get these sample sphere added into the our main firework. So we already had gravity that we were subtracting from the Y position, and then what we're doing with this time minus trigger time, we're basically asking how much time has passed since this point has been triggered. And then the maximum of 0 is basically saying, if it's a negative number, ignore it or just make it 0. So we can say trail position. I'm not going to use X or Y because I want this to be a 3D motion or random for each direction. And then we can do plus equals sample sphere uniform. And again, we just want this to be a random number, kind of like this. But we want this to be unique, different than this first random number that we created. If you remember like any of the earlier examples, if all of our random numbers are generated using the same seed or the same, basically they're given the same numbers, all of the results from your random function will be the same. If you don't want that, like sometimes it can cause artifacts or weird glitches if everything is synced up. So I just go ahead and type in some more slightly different random numbers. And if we go ahead and look at that, what we've done is just added the sample sphere uniform. We've just added like a uniformly random direction to the points. What we can do now is apply the same scaling over time. So we want this to increase the distance from the trail points from the source firework. So now they're all starting kind of at the, they're being emitted, and then they're just shooting in a random direction. So it's pretty cool. If we don't want these to be as fast as well, we could do some kind of multiplier like that, like we did with the gravity. So we have something like that. If we want to make that motion a little bit more interesting, how long does it take you to be this good in math? I never studied that much math. Is basically it's all from using just Houdini and doing effects over time. So just writing shaders and doing animating effects and stuff like that, you end up using a lot of these functions over and over again. I think Houdini is a pretty good software for like learning these functions, and you could use them in a lot of places and visualize them very nicely. So if we want to make our trail points a little bit more interesting, we have this sine function that we're using for the altitude or the height of our trajectory. We can do another function to influence how quickly these trail points like diffuse outwards. And this is going to be a repeat of the first week, or one of the functions we did in the first week. That would be the decay function. So with this u, we could look at 1 divided by u. Where we get this kind of like sloping thing that falls down over time. And we look at the exponent like that. And then you can see this makes it a little bit easier to work with. The maximum is going to be 1, and then it will just decrease over time, or as this u value goes on. So currently what we're doing with these points that are diffusing outwards is just taking this like linear function, or it's just basically, let's just take a look like this. This is going to be going the wrong way, but basically over time, these things, we could flip it around like this. Our trail points are starting at the kind of center of the firework, and then they're going away like that. Over time, it's just a kind of linear relationship. As time increases, the distance increases. If we use this decay function, you can get a little bit more kind of like damped drag, or like there's air resistance or things like that that affect how quickly the firework can travel away. We might actually want to Let me take a look at just switching this around. So I might use this power function. Works similarly, but instead of starting at 1 and decreasing to nearly 0, this starts at 0, and then over time we can change how it tails off. So if we go with a power of something less than 1, we can get another kind of shape like that. So this is our time. This is how much time has passed since our trigger has happened. And need a bigger window a little bit. If we do a power of something like that, you can see at the start of the trail's lifespan, it accelerates or it moves really quickly, and then it catches the like air resistance or something like that and falls off, slows down, deaccelerates. If we go the other way, this is something that will start slow and then get faster and faster over time. So back something like that. You can try other numbers if you want, but this thing should be pretty nice. And let's just do one more thing. And we'll do another condition for our if statement. And the way you can do that, I don't know if I've done this before on the stream yet, but if you use 2 ampersands, this will say if this condition is met as well as an additional condition. So if we look at our trail points right now, they are only being created if our global time has exceeded the time that we want to trigger these. But we also don't want to create them like if they've lived too long. Like we want to kind of hide them or not show them after enough time has passed. So what we can do is just add another condition that we need to meet to say that. So we're basically saying if time is greater than, or if if the global time has surpassed the trigger time, and it hasn't been too long. So let's say trigger time is less than the global time. Let me think about this a little bit more. So let's say time minus 1.2. So 1.2 is going to be the lifespan of these trail points. And it looks like I've messed it up. This should be the other condition. Done with the school semester. We're wrapping up our semester here with the Pure Vex. So you're about to be fully finished with every homework, every learning endeavor. So yeah, we're part of the way into this fireworks example. We're just finishing up building out the trail right now. This is the last week of this Pure Vex, so I'm planning just to do these 9 of them and wrap up with this one. We might do something else after this. We might do another topic or something like that. But just for this series, or to have a nice, concise kind of group of streams or workshops or whatever, I think 9 is a good number. It's kind of like the length of a semester. So we have it, so we use this double ampersand to do and. Another option you can do is these two pipes, the vertical bars or whatever. That's a different relationship between these two conditions, and that's or. So it's saying if this one or this one is met, it will allow these points to be created. So you can see that that way it never, one of these two conditions is always met. So the other thing is that both of these conditions have to be met to allow the code to be executed. Calling this logical and. All right. So this is our firework with trail points. If you guys want to get caught up, let me just do a quick little diffuse outwards. Let's get back here. Only creates when conditions are met. And you can do another file share if you guys want to get up to date. Now I'm just going to move forward with another duplicate of the code. And then I'm going to start cleaning things up a little bit just to stay organized. One thing that I usually like to do is, instead of hardwiring time like this, I'll usually first pass it to a variable. Just make a copy of it like that, and then replace it here and everywhere else that we've used it so far. So this way, if you need to randomize time per particle or just remap time, you can quickly globally multiply it or divide it or whatever to make it quicker or slower, or anything like that if you need to. And then we need to use it here. And I think that's everywhere that we've used it so far. Line 4. Ah, you caught me. All right. So it's a good thing to do this earlier on rather than later, because it can get like tedious if you start using this global variable everywhere, or the global. So what we can do now is just one line of code. If we want to have time be 4 times as slow, we can just globally remap it instead of each place doing like time divided by 4 or whatever. So just keeping our code clean, staying organized and that kind of stuff. Let's just think about what else we want to do. Another thing I can do is make maybe another variable that I'm going to call detonation time. I think I spelled that right. Right? Yeah, I think we did it. So this will be when the firework will explode. So I set it here at 2.5, but we can replace it. This is, again, just kind of keeping things clean. Yeah, so we'll be putting this other stuff into variables. So it just gives you a little bit more intention as to what you're using the code for. So we're saying if t exceeds or is greater than the detonation time, we don't need to draw it anymore, or we can remove it. What we're doing also here is a little bit more clear, because we're saying that the trigger time will happen randomly between 0 and the detonation time. So that's making things a little bit more clear. And I think we're okay for right now with the variable cleanup. We can also get rid of some of this repetition here. So 1.2 seconds as well. This one, I'm going to leave it in for a little bit. But yeah, that can be a good, we could clean it up if we want. So this will be, trail lifespan, and we could set that equal to 1.2. All right. So another thing we can do is that we're using the same sine equation in a couple places, here and here, and we're using them to compute the same value, but we're just feeding it like slightly different inputs. So that's something that we can clean up as well to stay a little bit more organized. If you want to keep using this global kind of trajectory equation, every burst point or trail point that we create, we're going to need to know like where we want to create it relative to the position of the fireworks trajectory or the path. So if we wrap this up into a nice little tool, it will make it easier to keep referring to it instead of like, again, if I wanted to change the horizontal movement of this, if I just change it here, everything will be decoupled because we need to keep remembering to change it down here. So one of the ways we can do that is a new technique if you're just following this course in sequential fashion. And that's going to be making our own function. So you can, like this sine function right here, charts or plots a one-dimensional kind of fluctuation in value. We can make our own kind of equations or functions. And what I can do is just call this projectile. And then if you want to make your own function, the way that you can do that is using parentheses. And then you do the Egyptian brackets. So inside of these parentheses is the arguments that the function will take. So like the sine function, this only takes one argument. It's just the position, the radian coordinates. And remove point, this takes two arguments. So it just depends on the function and how many arguments it takes. But you can make it take as many as you want. So with this, we're going to need a float, which will be the time of the projectile path. We're going to need to find out, when you add new arguments, you just use these semicolon. So we're going to need to know that. We can ask for the amplitude, the desired height of the projectile. And then I'll make one more that will be the frequency. That's what I'm going to call just the horizontal movement or motion. So like this, and this is kind of like changing the frequency of the sine wave. And then what you do with these functions is you just tell it what value it's going to return. So this should get clearer in a little bit, but let's just build this out quickly. So you get this to stop yelling at me. Anytime you call this projectile function, it will return this result, or the basically like this sine. This gets replaced with a single value or a single number. So we're just making our own equation or our own function similar to this sine. We're just starting it. We're saying use the starting position at 0, and then we can do these functions inside of our function up here. So you can use other functions inside of your function. It's kind of like a wrapper or consolidating things down a little bit. So we're going to say the position.x for this is like our local or individual, is just visible for when this function is running this variable. So the position will be t for time. Frequency over here, we can replace it. And the amplitude, we can get rid of that as well. Or we can include that in. So we have that. We can also do, I'm sorry, this should be the y position. And we'll have the x position. That's just t, or time, times the frequency. So I'm just recreating these. You can make functions and call them from any wrangle. The only way that you can do that, though, is by in your Houdini user directory. There's you could include like vex files in that folder. It's the same way if you look at the $HFS is where your current like Houdini directory is. So inside of this directory, they have a vex folder, I believe. Vex. And then inside of that, there is include. So all of these, some of them you might have seen people including them before or not, like this math, basically like extra functions that you can use. So if you wanted to make your own, this is just definitions of constants. But if we look at maybe like voplib.h, this one actually has some more interesting functions and stuff going on. So if you just make one of these files inside of your home directory, a vex include folder, then you can call them in wrangles. I tend not to like to do that too much, just because if you're redistributing Houdini files, everyone else who's going to open up your code or your Houdini file will need to also have those text files or the vex include files. I actually don't even use functions too often. It's even rarer than arrays will I use a function like this. And when I do, I'll end up, even if I do like use it often or everywhere, I'll just retype it or copy it into the wrangle node like this. If you were working at a bigger studio with like a bigger team of people and you all agree that you want to kind of maintain like a code base or something like that, then it would make sense to have your like studios like vex branch or library of functions. But just for an individual artist or individual user, I'll try not to make my own vex files too much. So what this is going to do now, we can replace our code here with the vex function. So let me just look up here, look down here. All right. So I got rid of the p.x and p.y. what I can actually do is just set the position using our projectile function like that. And then we just need to satisfy these arguments. So without it, it would yell at me. It will just say, you didn't include the proper floats. You need to provide this function 3 floats, and you didn't give it any floats. So if we just say t right here, we can basically pass our global time here to the function for it to use it as time. We can say that our amplitude, we'll just start it with 1. And then the frequency, we had been using 0.25 throughout down there. So we can do that. And now it will run. So we've basically wrapped up these 2 lines of code that we were kind of reusing. And for specificity, or just for clarity, we're saying this group of, these 2 lines of code, just call it the projectile function. And then anytime we want to look up a position on the projectile path, we just need to tell it what time we want to find, and then the other parameters that control the height and length of the projectile path. So we can do the same thing down here, and we'll just say the trail position will be equal to, you can copy this, paste it here, and again, instead of t, we just want to find the fixed position on the path when we make a trail. So we replace it, and visually, let's take a look here. I guess I did change my horizontal offset there. So like globally, if we're going to change the horizontal offset, we can do this in one place, like that. Looks like I'm a little bit less of it. Might be a bit off topic, but still new to Vex. Are there any ways to debug line by line in Vex? See what variables contains. I'm not sure what type of, if you're talking about like a code IDE or a like standalone application for developing code, Vex doesn't give you, the Wrangle interface doesn't give you that much ability to like step through it line by line. If you're interested in debugging things, what I've usually done is assigned the value that I'm interested in debugging to a attribute. So if I do like f at a, so I usually use capital A because this geometry spreadsheet shows up in alphabetical order. So if you do A, it should show up right after P. The position is special because it's the point position. It always exists, so it will always be the first thing that it shows. But if I just want to check what time is, this is how I'll like debug or visualize that variable. So this is how I'll usually check it. If you're getting compile errors, you have some weird syntax or something like that, you'll get the red squiggly line. If you middle mouse button on the node, it will tell you the first line that it finds an error in. If you do more weird like errors and stuff like that, it will just like, you'll just have to individually fix these problems. So like here it's saying it expected an equal sign after my variable declaration, but it got a weird equation. So if I fix that, then I can middle mouse on here again. Now I see there's a syntax error at line 13, character 31. If you look at the bottom right of your syntax editor here, you can see like the address of your carriage or the text highlighter. So if I middle mouse here, I can see it was expecting a semicolon, or I didn't end a line at line 13, character 31. So it's saying basically 1331 right here, there should be a semicolon. Can add that in. And then there's one more error that I made some numbers after the bracket. This one, it might not be as clear. Might be having trouble. But you get the idea, is basically like somewhere in this area you messed up something. All right. So we're back to working functional order. Do another file share. This will be cleaner code. So basically, these two were getting visually identical results. But if we look at the code between the two of these, this might be a little bit longer to read, but overall it's a little bit more clean. We've gotten rid of like a lot of these random numbers, and when we do use a number like that, we've just used it in one place only. So like up here, when I was changing the horizontal distance that things would travel in, I was just setting it up here and then down here. So if I wanted to change the horizontal distance traveled, I would have to update both these two lines of code. But now we've consolidated all of the projectile movement into a single function, and then we can reuse this bit of code in more than one place if we want. So hopefully this is making sense so far. Sorry if I'm moving a little quickly or stumbling through some of this. So this is our function to return a position on the path of the ballistic. The reason I use ballistic or whatever, like this ballistic projectile, this is a pretty common like physics problem or equation or stuff like that. So ballistics is just a English math like kind of term or whatever. You can read about all this kind of stuff on Wikipedia or whatever. There's other very elaborate Greek alphabets and codes and stuff like that. So we just have this wrapper that we've made, and we can ask it. We can say at any given time, amplitude and frequency, where will this point be on the path, the position on the path of the trajectory. We have that. This is our time of firework. Sorry. Detonation. Just say this is like the current time. This is the detonation time. So this is kind of like when you see NASA, when they're going to launch a rocket or something like that, they'll say like T minus 12, T minus 10 or whatever. They're basically counting down from T to the liftoff time or whatever. So that's where that comes from, is like using variables and using scientific functions and stuff. T minus 8, they're saying it's going to lift off in 8 seconds. We did a similar thing in these lines of code. We were saying like T minus trigger time. This is like T minus 8, or similar to how a rocket, they talk about when a rocket is going to launch or that kind of stuff. Let's just make one more variable here. That will be we'll just call it trigger life. So what I'm trying to do here is just replace this bit of code that I've used in a few places. So we have the time that the trigger will start at, the trail point, and then this is like the current, how long it's been alive for is the trigger life. So we're basically using this to drive gravity. We're subtracting from the altitude or the height by the length of time that it's been alive for. And then the main reason I did that was so that we could replace it. So again, we're not doing the same equation or this bit of code over and over again. This is pretty cool. We've cleaned up our nice little framework or whatever. This is time that the trail point has lived for. This will be time that trail point is created. And then this is the starting position of the trail point. All right. So we should be good. Let's move forward and keep building this out a little bit. So just make a copy of it. We can think about how we're going to make our explosion now with the burst. So we've gotten the first majority of our particle done, or firework. Now we can make our spherical burst. Just thinking about that, you should already see some similarities. We can reuse this sample sphere uniform function again to draw our kind of bulb. We can normalize it if we want it to be on the outside of the sphere, or all the points the same distance, or we can leave it random if we want to just have random directions or random lengths inside of the sphere. So we use a for loop here to do our trail point generation. I can just copy it and paste it. And then this will be our burst point generation. So we have control over how many trail points will be created over the lifespan of the firework. We also have control down here. If we want like 8 times as much burst points or blossoms or whatever, we could do that, or we could change it. We just have additional flexibility like that. So we did that. Let's see how we want to decide whether to show the explosion or not. We'll do that with another if statement. And we'll do our Egyptian brackets. So for the if statement, what we want to check is if the, let's see if this, I think it should work. Time has surpassed the detonation time, right? If the global time of the firework has exceeded when we're going to detonate it, then we want to start drawing or start our blossom or our burst routine or our burst line of code. Do all this stuff if we're past when we've detonated. So that should be good. Again, we'll make a vector. So before we were doing the trail position and just starting it at 0, what we can do here is the burst position and just start it at 0. So we've created, we haven't even created the points yet. We've just set up our framework. So we can keep going, keep building this out for a little bit. All right. So we'll do the add point function. That will be 0 again for this geometry or this current geometry. And we can use the burst position. So again, all this burst points should be at the origin or at 0. And you can see they don't appear until we're after the time. So just looking overall, we kind of have what we're after. We're getting closer. Once this thing detonates, we created a bunch of points at the origin. What we want to do is create them at the detonation point of the ballistic, and then we want to move them uniformly outwards or expand them outwards. So we're lucky we have our nice function that we made that we can use to look up any position along the projectile trajectory. So what we can do is say the burst position equals, use our projectile function. And again, this, instead of trigger time, we can use the detonation time. So pop that in for the first argument, the time of the projectile path we want to find. And then we just need to reuse the other arguments. So we're using 1 for the amplitude or the height, and then 0.25 for the frequency. And something happened? Nothing happened. Okay. I was on the wrong frame. So now that I put that in, all of our burst points get created at the detonation point, with the explosion point of our ballistic path. But we haven't moved them or anything like that. So we just need to do reuse or repeat some of the code. We have this gravity function. We have the trigger life. We can reuse that, but instead of this being trigger, we just call this maybe burst or detonation. Time that the burst has lasted for. And then instead of this being t minus the trigger time, this should be t minus the detonation time. So we're just saying how much time has passed since the detonation point. And again, we're doing the maximum of 0. This just clamps any negative numbers. So maximum uses the highest of these two arguments. If we have a negative number, it will use 0 instead of the negative number. So that's pretty cool. We can then go ahead and add our gravity. So if we just take our burst position with the y component or the altitude of it, and subtract the detonation life, let's just try that. And it looks like it's working. So it's just really heavy or really big gravity. Again, up here, the trail points, we were multiplying that by 0.1 to just basically do less gravity. With these burst points, we could do like even less. Sometimes you don't expect them to fall that quickly. It's like a little bit different than the trail points. Maybe they're lighter weight explosives or whatever you want to think of it as, the mortar or the glowing bits or whatever. So we have our gravity again. And then we just need to, again, do a similar thing with this diffusion outwards. So we'll take our burst position and add to itself the sample sphere uniform. Again, we want to sample a random position of the sphere. So we'll just do a new random number using something, the point number, and again, we can use the I, or the iteration of this loop. So for each burst point that we create, it will have a unique position on this sphere that we're sampling. So we'll do I times some number. So once we pop that in, we get our burst, but it's not moving. So we just need to scale this burst shape over time, or over the detonation life. So we just multiply this by the detonation life, and then we have something like that. But this is a little bit unrealistic. You would see, like we were doing with the trail points, we were using this power function to get like a kind of logarithmic or like exponential decay. We can use a similar function. So we want to dampen the detonation life over time. So if we do something like 0.045, then we get a more interesting kind of, looks more like a firework. So this big explosive burst at the start, and then the fuel or the thrust wears off, the air resistance or something like that catches up to it, and it quickly deaccelerates. We might also want to do what we were looking at over here with this normalize. So when these main bursts happen, it seems like they all get kind of, it's hard to tell in like 3D or whatever, but uniformly, like a dandelion, like seed pod or whatever, these all get propelled with the same thrust or the same distance. So if we do normalize here, what we're basically doing is removing the individual unique speed or length of these directions, and we're just saying to make them all the same. So if we go here and normalize this direction, now we have more interesting sphere like that. And we might want to just multiply this by something like 25.25, like 25%. This is just like a global size of the burst. So if you want to change that, you could set it to something different. If you really want to keep clean with everything, you could have like another float that will be burst size, like that. So just keeping things a little bit more legible. So it's pretty cool. We also need to turn off or remove these burst points after a certain amount of time so that they aren't just drifting around forever. So what we can do is do our double ampersand, two and symbols. And what we also want to compare against is if we've surpassed this detonation time by a certain amount of time. So like here we were doing trigger time is greater than t minus trail lifespan. We can do another thing where the t minus, this is going to be our detonation lifespan. I haven't named it yet, but we can create it in a little bit. We could say that the burst is going to last for 1.25 seconds, and we can take our detonation time and subtract it. Or, I'm sorry, we want to do a comparison like that. So after 1.25 seconds, we no longer meet both of these conditions. And we don't end up drawing the point or doing any of the math or calling any of these lines of code. So if we want to keep things organized, we can say we have a burst lifespan and set that to 1.25. And then just add this and replace it. So this is our firework with trail and burst. If you want to get caught up or you're running behind or anything like that, do another file update. And we're rolling. we're exploding. So we've gotten most of the way there. We just need to add some interesting kind of visualizer or augmentation. So we did a little bit of that before. I don't know how much we did, but here when we were setting like the radius of each sphere, we did it. We used it here, maybe setting the p scale or the luminance or the intensity. We can do the same thing here with the set point attribute function. So what I'm going to do is record the point number. This will be our burst PT. And then I can refer to this point number later on and say set points attribute. You want to do 0 again for the current geometry. We want to tell it the attribute we're setting, which will just be CD. This is a default, like built into Houdini attribute. It stands for color diffuse. It always needs to be capital C, lowercase d. I just use it because it's built in for what the viewport picks up or automatically displays. And then we'll say which point we want to be setting the color of, or the attribute of. And then last is the value. So if I just say vector 5, something like that. Once these get created, you can see all the other colors get initialized or default to 1. But then if we find any of the burst points down here, they get set to 5. So that's kind of cool, but we want it to be a little bit more interesting. So what we can do is look at our detonation life for how long these have been alive for. And we can use a sine function based off of that detonation life. So it's a little bit too slow of a sine function frequency. You can see it's starting at 0 and starting to like fade up or cycle up. What we're viewing is just the first, we're just viewing like this much of a sine wave. So if we want it to flicker or pulse more, we need to increase the frequency like that. And then that will determine how many cycles, how many on-offs, how many like flickers of the color we generate. So you could multiply it by 24. And then you can see it's flickering. But everything is synced up. So if we don't want to sync things up, we can just add some randomness. So like we did here, where each burst point that we create, or each iteration of this loop, we sample a different position of the sphere. We can do a similar thing and basically sample a different position along the sine wave. So we have that. We want to do a different kind of unique random. And then I think we're going to have to multiply this by pi and by 2. So we're getting different positions along the sine. If you don't multiply it by 2 pi, your particles or the color will still be synced up. You'd see that a little bit. They're a little bit different, but not different enough that like visually, like some are only turning off quicker than others, but it's not a complete cycle. So like up here with our sine function, if we just look at that, we've only offset along the sine function by this much. So if you multiply this by pi, then you have a half cycle. If you multiply by 2 pi, then you have a full duration. So by multiplying this by 2 pi, what we're saying is offset them or randomly reposition them anywhere between 0 and 1 cycle of a sine wave. Without the 2 pi, you're saying only offset them by like what would be roughly like 1/6 or 1/7 of a sine function. So they all appear too synced up. We have some better randomness now. We might want to do even a little bit more flickering. Just depends. Can do less as well. It just depends on what you're after. So that's pretty cool. We have our burst points being visualized. What we can also do is we want to do some point color modulation of the trail points. So I'm going to add the Egyptian brackets to this if statement. Then we can add more than one line of code to be executed during the if statement. So we'll say our trail point is equal to the point number when this is added. Did too many equal signs there. Got carried away. So we can also set the color or the point attribute. So like just by default, if we wanted to set the color of all of the trail points to something like 0.225, we could try that out and see how it looks. So you'd see we kind of faded them out. We just don't show them as bright. Can do something even closer to black. This is more like a smoke or soot or something like that. There's something you barely see. But what we actually want to do that could be a little bit more interesting is we just want to look at the trigger life. So if we use this inside of here, then we get some kind of like thrust. So basically, we kind of fade them out so they're not as bright, and then they get more intense or brighter right before they die out. You do other visualization styles or stuff like that. You could flicker these or do other interesting stuff as well. But I think this is a nice visualization. So that's pretty cool. Moving along, let's get into the end here. So we can wrap this up and build this out to function with more than one source point. We can add some more variance to everything, and see how far we can get. So we'll do another file update. I'm going to copy this, but I'm going to shake it free. And what we can do with it is connect a grid. And then everything here is just still getting placed at the center. So there's a few things I need to do. Instead of overwriting P with the projectile, I just want to add that to it. So we're offsetting the point position by the projectile path instead of overwriting it. I also am just going to, actually this is going to be a little bit easier. So if I go to my grid, instead of polygons, I can just have it create points like that. And down here with these trail positions and stuff like that, let's make another variable. So this will be, let's just call this the launch position, and we'll put a copy of the source point position into the launch position. So then when we do all of our trailing points, instead of having them start at 0, we can have them start at the launch position. And instead of overwriting it with the projectile, we want to offset or add the projectile motion to itself. And then we have some unique trails, but the burst is still at the middle. So if we do the same thing here with our burst position, we want to start that at the launch, and then the projectile motion, we want to add it to the burst position instead of offsetting it. So then we have a bunch of identical looking fireworks. So if we want to make this a little bit more interesting, we want to keep adding some more variance and stuff to everything. So with this burst lifespan, we can multiply this again by this random numbers that we were generating. So we'll say random number based off of the point number just multiply this by a number and subtract I, and then just add some number to that. So now when we see the burst, certain burst points will die off quicker than others. So without this, let's just add our semicolon and comment out. All of these live the same length of time and die immediately. But we can add some variance to that, just to make that a little bit more interesting. Let's take a look at what we can also change. So the amplitude here, we were always using 1 throughout. We could have some randomness so that our fireworks go different heights. So let's do a float, firework height, set it equal to a random number. This one just needs to be unique for each point number. Does that stuff kind of make sense? Like, this globally is just going to be a different height for each firework. We don't want it to be different, like different heights for all of the burst or the trail points. So we just need to use this point number. And we can say 1 was originally our amplitude. So if we add a random, we can remap this random. If you do fit 0, 1, this is a handy remapping function. It expects a value in the range of 0 to 1. So it already knows the random number that you're giving it. You don't need to remap the input. You're only setting the output range. So we can say negative 0.2 and positive 0.2. So what we're going to end up with once we finish putting this in is firework heights with anything between 0.8 and 1.2. S. Wash, thank you for the 2 months. Twitch Prime, let's go. Thanks for bearing with this stumbling through the code. So we can wire in our firework height. And we want to replace any part of the projectile function we had with just 1. And we can replace that with our firework height. And now we have a little bit of variance or randomness. If we want to increase the horizontal movement, I can just go up here to the top and globally set that. So what we did here is everything is traveling in the same horizontal direction. But that's something we want to rotate or randomly spin around as well. So what we can do with that, we're going to be breaking out all the the tools in our toolbox. So with this warping, and afterwards we were using a bit of the matrix operation to store like a local transformation. We can do the same thing here. So let's just do a matrix. There will be we'll just call it X form for transform. And we'll initialize it to the identity transform. It's basically a uniform. We just start it with a scale of 1, no translate and no rotation. But then I can add my own rotation to it. So we're rotating our transform matrix and the amount that we want to rotate it. Again, this is in radians kind of like the sine function. So we want to do a random number unique to each point number. Just add another random offset to that and scale it by 2 pi. So we have that. And then the axis that we want to rotate around will just be y. So just top down like that. We're looking down the y-axis, we just want to rotate each firework randomly like that. So we can apply this transformation anywhere that we're setting the point position. We can multiply. So we'll say P equals P times transform. But you can see when we rotated there, every source point, we're not looking at the rest of the code yet, but every source point got rotated randomly, but it didn't stay in its original position. So when you apply a transform like this, you need to make sure you do it at the origin, or you're basically influencing the pivot point. So what we want to do is take P, and we want to subtract the launch position, or the starting position, do our rotation relative to the launch position, and then move back according to the launch position. So then everything ended up back where it was, but the trajectory is now rotated randomly based off of the launch position. Instead of without doing this, you're basically treating everything like the pivot point is the origin. So by moving, didn't want to do that. So by moving all of these, or rotating them relative to the launch point, we're basically saying use the launch position as the pivot location. We just need to do the same stuff for the other points that we're creating. So before we add this trail position, we can do this maybe all in the same line of code. So we're going to do trail position minus the launch position. Do the parentheses for order of operations. So we're basically saying do this translation first, then rotate, then move back to the original. And now we have our trail randomly rotated. So we'll keep going. We'll do our burst points. Just need to do the same modification here with the burst position. I can just grab this line of code and we'll replace it like that. But instead of the trail, this is going to be the burst position. So now our burst positions are offset randomly as well. If we want to make another little improvement, we can change the global time up here. We could say t minus equals a random number based off of the point number again. Something like that. So we want some fireworks starting sooner rather than later. Again, if we have stuff going into negative numbers or beneath the ground, we can use the minimum function. So we're doing down here, or I'm sorry, the maximum function. Use the higher number between 0 and t minus the trigger time. So if we do the same thing here of t equals the maximum or the higher number of 0 or t, we'll basically say if t is less than 0, use 0 instead of t, just to keep everything from starting or going below the ground. We might want more randomness for the heights, just to get stuff a little bit more interesting. And then we have a pretty nice display, a pretty nice finale. If you're following along, you can do another file update. And we'll just do one very last thing. If you have any questions as well, feel free to drop them in. So the last thing we're going to do is just add these colors in. If you remember from last week with the arrays, we used arrays during that workshop to store a library or a list of color options. So we can do the same thing with these fireworks. So you look at this illustration. There's a lot of special or unique compounds that get used to make these explosions, different salts or stuff. You do if you're a chemistry major. What we're going to do is just specify some different RGB colors to differentiate the explosion. So at the very top, doesn't really matter where you declare it. You can just make vector colors. Then we use the square brackets to indicate that we're going to be making an array attribute. If we want to fill it with values, we can use these Egyptian brackets again. You basically use one set to specify the start and end of the array, and then inside of those, each one of these will indicate another vector or another color to add. Maya animation, thank you. I'm glad to hear you're enjoying the learning experience. It's nice to hear encouragement or feedback from people. So if we want red, we can just do this. Whoops. All right. And we made a mistake. So again, you can do middle mouse button. You can see it was expecting a semicolon. You can add it in. So it's not too useful right now with the colors just being a single value in the array. So if I want to add another option, we can do that. I'm just going to move the one over to the third component. So we have RGB for 1 for red, and then blue. So red is 0, green is 0, and blue is 1. And then I'm only going to have these colors influence the burst. And when I specify the color attribute for the burst points, what I can do is say colors, use the square brackets again here to find an item or retrieve an item from the array, and then we can multiply to color or apply the color. So we've basically set all of the burst colors to the 0th, or the first entry of the array. If we keep going, we can find the next index is the blue. If we want to retrieve randomly a number or a item from the array, we can use the random function. This is going to be based off of just the point number. Because again, we don't want it to be unique. We don't want like some of the burst points to be red and some to be blue. We want all of the fireworks to be a single value. No way, it's the last one. It's been quite a journey. Yeah, hopefully it's useful for people to get deeper into Vex. I don't know, a lot of the material that I see out there is mainly like a glossary or like instruction manuals or stuff like that. So hopefully these little kind of challenges or workshops or whatever are cool to visually see some interesting stuff as you're plowing through it. Code in itself is already pretty boring and dry, so hopefully this is making it a little more interesting. So we get a green squiggly line here. This is like a warning. Basically, we're saying this random number is a float or a decimal. It's a fractional value between 0 and 1. There's this insane one by Animatrix. Yeah, the pragmatic Vex. That's a really useful one for like tool building or stuff like that. That's definitely not an introduction. So my thought process here with these is getting people who haven't been familiar writing code or programming in the thought process of kind of a programmer, familiar with variables, just the overall syntax of Vex, and using functions and stuff like that. But the Animatrix one is super useful if you're really looking to kind of apply this knowledge to build tools, build really powerful things using Vex. So kind of working with existing data, his stuff is really great for like analyzing meshes, doing all kinds of fancy stuff given input data. This stuff I'm doing here is more of just like a sandbox of like starting with nothing. Let's see kind of how code works and where we can get ourselves up to. So we're generating a fractional number here between 0 and 1. What I want to do is just look at the floor, or to round it down to the lower whole number. And then the warning goes away, but we've rounded down a fractional number, so it's always going to be 0. So we just need to scale it based off of the length of the array, or how many colors we have in our array. And then it will automatically adapt, so that we get some red and some blue. If we look back at our sheet, we have some orange ones, yellow, green. We can go in and just quickly add them. We'll do a green one like that. Some of them show up green. We can do a yellow one. You do 110 to get yellow. You can do an orange one. So orange is between red and yellow. So you can do something like that to get orange. And we can also do a white one. So we didn't get all of them, but we're a little bit closer. These colors aren't that great in terms of like visual results. You might want to do some color sampling or stuff like that to find out a little bit more like artistically friendly colors. Another thing you can do is multiply these. So if we say like 4 times, oof. I don't know how that warning came up. All right. So you kind of overexposing this, like it's blowing out the intensity. And sometimes you could add like a little bit to get yourself away from like a fully saturated color. And then when stuff burns out, it won't be fully like crisp or whatever, too overly saturated. So you get a little bit of a different color variation. Jabram, how's it going? Catch up on the VOD. Yeah, it's a bit of a it's a bit of a long one. You're typing a lot of code. But yeah, the idea, we're just finishing up now. But yeah, we're putting together a lot of the previous examples of functions, ideas, and stuff like that. There is some new concepts we did today with this custom function. We created our own function inside of Vex. And we were also doing like these bigger conditionals using the ampersands, basically saying when both conditions are met, do execute the code inside of them. So it's a bit of a review, but there's also some newer stuff as well. Probably too much stuff, but keep going. So I'm just tweaking these colors right now. So if you just get these away from like fully saturated, just by adding a little bit of color to the other components, you'll get a little bit more natural looking results. So I think the orange one is okay and the white one is okay. Good for the, yeah, it worked out. It's a little bit of a celebration finale for the final one. Probably do some other series or workshops or stuff like this, but I just felt like this format with the constraints I was doing for these to build everything using a single wrangle. It's a good way to introduce yourself to Vex, but it was getting a little bit repetitive, or I don't know. It's a good practice for people, but it's cool to move on to other ideas and other parts of Houdini as well. Like it was a bit limiting to always start from scratch and do everything in a single wrangle. It's a cool challenge. It's fun to do, but 9 of them is probably more than enough for everyone. All right. So we have some fun stuff happening there. Yes, I think we're close to being done. What do you guys think? If you want to do one of the classic tricks I was always doing, I think I did it with the rain, a few other ones. If you want to loop time, we can do that using the frac function. So this gives you the fractional result of t. Basically, after it surpasses 1, it starts again at 0. So instead of going like 0, 0.5, 1, 1.5, it just keeps going, repeating between 0 and 1. If you want to graph any of this stuff as you're learning or you're figuring this stuff out, it's helpful. I end up doing this stuff all the time, even today. So if we look at sine, instead of that, we look at the frac function. This no longer works in radians. So just 2, this is like 2 repetitions. If you don't do the frac, then you get the full result. So we have that. Again, we'll look at the frac. The way to think about it, this is kind of looping time, because you keep repeating the same values. You keep outputting the same values. So we're just repeating from 0 to 1 seconds. If we want to scale that a little bit differently, what we want to do is like divide it by 6 and then multiply by 6. So you do that to keep looping or to keep repeating anywhere from 0 to 6 seconds. I think we want to do this after the time offset. So now if we offset like by 6 seconds, then we'll just constantly get exploding fireworks. Everlasting fireworks. So we'll do another save, another file update. But yeah, that's pretty much all that I had planned for today.